Well, hello there. Look who came to class today. I don't know. I got to start my videos with something other than because I don't like all of my tics that I have for nervousness and whatever. So we are just working a few problems today, right? Those problems on page 823 will definitely work better for you if we do the problems. You try the problems first, and then we look at them together. As of right now, I'm assuming we are not coming back to school, so we're going to try and do everything this way. So we're going to we'll be slowed down a little bit because we won't have as much in-class review time and stuff, getting ready for the AP test and all that kind of stuff. I'm not sure what their plans are for the AP test. I know the College Board cares about money, and so I doubt they're going to cancel it or whatever. But anyway, let's go ahead and work a few problems. So number 16, hopefully you've got a book and you're looking at the same thing with me, because I'm not going to be able to draw all of that. Oh, don't point it at the microphone. All of that on the board. But we'll walk through those together. 16A, rank the reactions from fastest to slowest and explain your answer. If you have any reactions of equal rates, explain why. So fastest is that's not going to be endothermic, exothermic. That's kinetics, right? And kinetics is about activation energy. So I'm going to look at the activation energies. So I see they all start at the same spot. So basically, whoever has the lowest activated complex, which would be 5, that purple one has the lowest activated complex. Then it looks like 1 and 2 have about the same activation energy. 4 might be the same. 1, 2, and 4. Yeah, 1, 2, and 4 all go up to the same height. So I would say those would all be the same speed, and 3 would be the slowest. 4 is endothermic, but that doesn't matter when it comes to kinetics, right? What matters is the activation energy. B, label your reactions as endothermic or exothermic and support your answer. Well, everybody but 4 is exothermic because they all go down as you go, right? So they start higher and end lower, so that is exothermic. The 4 starts lower and ends higher, so that is endothermic, right? The only one that would be endothermic would be 4, that blue line there. Rank the exothermic reactions from greatest to least change in potential energy. So 2 and 5 would be the greatest change in potential energy because they start at the same spot and end the lowest. And then 1 and 3 would be the next most exothermic because they start at the same spot and end at the same spot. There again, I'm not concerned with the activation energy because that's just endothermic and exothermic stuff, right? So there's 16. 17, given the following illustration, what can be said about the delta S for the process of solid NaCl dissolving in water? What can be said about delta H for the process? So we can say, when we look at the pictures, you've got a nice organized crystal lattice in the first picture where there's the solid, and then in the dissolved, they're all spreading around. Well, that is a lot more random when they're all spread around and whatnot. So that tells us that is more random when it dissolves. So delta S would be a positive because more random is a positive on that. That leads to a spontaneous process. What can be said about delta H for this process? Based on the information they gave us, nothing. We don't know. If it gets warmer, right, then it's exothermic. If it gets colder, then it's endothermic. Table salt actually will get colder, so it's endothermic, which is why you sprinkle salt all over ice cream, not the ice cream itself, but the ice. When you're making homemade ice cream, if you've ever done that, you put a lot of salt on it because that is actually an endothermic process, so it'll actually make it colder, and it makes the water freeze at a lower temperature. So it actually gets the whole system colder than it would be otherwise, and so it works better for making ice cream. Right, 24 at 1500 degrees or 1500 Kelvin, not degrees Kelvin, right? Because it's Kelvin. The process I2 gas goes to 2I gas is not spontaneous. However, at 0.1 atmospheres, it is spontaneous, and it's at the same temperature and all that kind of stuff. So at high pressures, you're not going to want to go to more particles, right? That's just It's probably easier to explain that from Le Chatelier's principle point of view, but you're not going to want to go to more particles at a higher pressure. Because it's going to be more random, but you're already at such a high pressure, you're breaking down into more particles, and so that's not going to be a favored process. Whereas when you're at a really low pressure, it is favored. kind of like when water evaporates. If it's really humid, it's not going to evaporate very quickly. If it's very, very dry, it's going to evaporate much more quickly, right? Same kind of thought process there. There's probably other ways that we could talk about that, but in general, it is the pressure is leading to high pressure. You're going to want fewer particles. Low pressure, you're going to want more particles. Right? 25. Which of the following processes would be are spontaneous? Salt dissolves in water. Sure, that's spontaneous. That'll happen on its own. A clear solution becomes a uniform color after a few drops of dye are added. Yeah, that's diffusion, random motions of particles. Iron rust. Yep, iron rusting is a spontaneous process because if you just set iron out, it will rust over time. It's not a fast process, but it is a spontaneous one. So that's why we have to cover it and paint and that kind of stuff to keep that from happening. You clean your room. That is not spontaneous. You have to add energy to that to make it happen. You have to force that to take place and that kind of stuff, right? There you go. 25. 28. Consider the following illustration of 6 molecules of a gas in a 2-flask bulb. What is the most likely arrangement of molecules? How many microstates are there for this arrangement? So this is one where it's a few more to draw than like 4 molecules. We can do it mathematically pretty quick. This, what's the B part? Determine the probability of finding the gas in the most likely arrangement. So you've got 6. Wow. 1, 2, 3, 4, 5, 6, all in one. That would be 1. And then every time we come over to this one, right, we move one of those over here. So now there are going to be 5 different arrangements where there's 1 over here. So there's 1 arrangement like this. There are 5 different arrangements like this where I could have the 1 over here or the 2 over here or the 3 over here or the 4 over here or the 5 over here, right? There are 1, 2, 3, 4, 5, 6. There are, let's see, how would we figure numbers on that one? Because there are 4 here and 2 here. But it would be 6 with every other number and 5 with every other number. That's a factorial thing, isn't it? Is that a factorial thing? Okay, so for each one, you're going to go 1 over 2 to the n, and there are 6 particles. So for every individual state, there's 1 over 2 to the n. So there are 2 to the 6. So 1 divided by 2 raised to the 6. So there is a 1.5% chance for each one of these because there are 2 to the 6 different things. No, not 2 divided by 6, 2 raised to the 6. There are 64 different possible arrangements, right? So each one of the possible arrangements gives us that. So so I got myself good and confused. I had to take a second and reset myself there. So we've got 6 different molecules, right? We've got 6 molecules. So 2 to the 6th is 64. So there are 64 different microstates that can happen here, right? It is very unlikely to be this. There's only 1 of 64 microstates will get you that. 1 of 64 microstates will get you where they're all in the right flask. They are proportionally more likely to be somewhere where they're not all on one side. So there are 5 different microstates that could get you this. There are 15 that could get you this, right? 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6, right? And so on. And there are 15 microstates that can get you this one. So then there's 22 that can get you this one. So you are significantly more likely to get one of these 3 where they're spread out evenly or almost evenly, right? Because you can just go like 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6, and so on, right? Until you get through to 22 different ones. So 64 total microstates, right? All right, so that's 28. The idea behind that one is more important than being able to do the calculations. Really, the only calculation I've ever seen anybody ask to do at our level is like this one where you say, what's the chances that they're all on one side, which you just do 1 over 2 to however many particles that is, right? Because there's a 50-50 chance each particle's in both sides, right? Let's see, 20 or 34. 34. Calculate delta S of the surroundings of the following reactions at 25 degrees Celsius and 1 atmosphere of pressure. So delta S of the surroundings, whenever I see delta S of surroundings, I jump back to that. Okay, so the system is going to gain or lose randomness or whatever, but the surroundings is going to gain or lose randomness based on the heat. because if heat flows out of the system, if it's exothermic, then that means you have made the system more disordered. So that's a positive delta S. If it is a endothermic reaction, then the system had to give energy to it, so that is a negative delta S. So it is harder on the surroundings as far as randomness and spontaneous and all that kind of stuff. So 34 gives us a reaction of propane and oxygen goes to CO2 and H2O, and I'm not bothering to balance it because none of that's going to be important, but the delta H is a negative 2,221 kilojoules per mole, and this is happening at 25 degrees Celsius. Right, so this is an exothermic process. So that means it's going to make the surroundings more disordered, right? So if it is more disordered, we're going to go delta S equals delta H, negative delta H over T. So that's going to be a negative 2,221 kilojoules per mole divided by, this was at 25 degrees Celsius, so we've got to change that to Kelvin. So that's 298 Kelvin. That turns into a positive, which should make sense because the surroundings will be more disordered. So 221 divided by 298, our delta S of surroundings is 7.45 kilojoules per mole Kelvin. Right? Not too hard. So that means the surroundings are going to favor this reaction happening. As we also look at that, if we want to, we can probably assess that this is going to become more disordered, right? So that's one big molecule. Elements are pretty low entropy. And then I've got smaller molecules and more of them. I didn't write them up there, but more of them. So probably a positive delta S. So a positive delta S, that means it's becoming more disordered. Heat energy is being released, making the surroundings more disordered. So everybody's becoming more disordered. So that's probably going to be spontaneous at all temperatures. It is spontaneous at all temperatures, but propane doesn't just blow up on its own. It does have an activation energy that has to happen. So I think that's a nice example of, propane will burn spontaneously at all temperatures, but you've got to get it going, right? It needs a spark or something like that, right? To overcome that activation energy. B, NO2 goes to NO and O2 gas. NO2, right? Not NO. Yeah, NO2. 2 NO2 goes to NO and O2, and there's a 2 there. And delta H here, I believe, was endothermic. Yeah, that was a positive 112 kilojoules per mole. And this is also happening at 25 degrees Celsius. So I'm going to do the same thing we did before. Delta S of surroundings equals negative of 112 kilojoules per mole divided by 298. So this is going to give us a negative delta S. So that means the surroundings are going to become more ordered. It's going to get colder. That's going to lead to it not happening as well. So 112 divided by 298 gives us a negative 0.375 kilojoules per mole Kelvin. So the surroundings are leading us to this not happening. So the only time that this might be spontaneous would be if we can make this factor less. So we drive down this whole factor by making temperature higher and higher, right? Again, endothermic things make sense that they would be more likely to happen at a higher temperature. All right, hopefully that helps on that regard. We should still be working through our OWL questions and stuff. If we're having trouble with those, that's what that afternoon time is for.